Hello everyone. We are going to look for the problem solution in the chapter 12. Uh, chapter 12 deals with the sources of a magnetic fields. That means usually it's a current source, and then how this current source is going to generate various types of magnetic field. That's our concern. Okay, so the first problem, two long parallel wires shown in the accompanying figure carry currents in the same directions. So I1 and I2 is given. What is the magnetic field at the point P here? So here is the case. Point P. So in this case, we want the magnetic field at the point P due to the two long wires. So we need to think about how those wire is generating magnetic field, and then we will see how it goes. The first thing is that we need to understand the formula for the magnetic field, okay, here. And then we have a two wire source, the I1 and I2. They are in the same directions. And you will see that if it is the same directions, we are going through those right-hand rule, okay, so that in this case, I1 will give the magnetic field point outward, okay, and as well as the I2 will give the pointing outward, so that here is the case at point due to the right of the B1 points out of the pages, and then the point to the left of the wire to B2 points into the pages, so that they are in the different directions. Okay, so remember that it is pointing. If you can write it. Okay, let me just try. So let me draw what it is. So around this loop, so it is out of the page in the B1. But in the case of this wire, you'll see that it is in this way, so that it is into the pages. Into the pages. That means B1 and B2 is in the opposite directions. Okay. Therefore, the net magnitude is given by B2 minus B1, so the absolute magnitude. And then it is given by this one. Note that is subtracted. And then if you just plug in all the things, then you may get the right magnetic field. But the thing is that you have to have a right unit. Okay, so I in current, I is in ampere, and then this distance R should be in meter. Okay, that's the key point. And now let's look at the another cases. The accompanying figure shows two long straight horizontal wires that are parallel, and the distance are 2a. 2a. If both wires carry current I over 17 ampere, 17 ampere here, 17 ampere there. What is the magnitude of the magnetic field at point P2? Okay. So A is given, A is 5 centimeters. So we need to find out uh, magnetic field at this point P2, which is B1, vector plus B2. So let's look at how the direction is concerned, so that on this, it goes like this. And then, so that the B1 is into the page. But in the case of I here, so let's look at once again. It is going to be like this. Then this is going to be the same, okay, into the page. Okay, so that we know the magnetic field generated by the straight wire carrying current I is given by this one. And the direction is, if there's a I, and then it's going to be like this. And depending on R1, R2, okay? And so here is the case. We need to find out the distance, so that is R. So in the case of a distance to the lower wire, from here to here, it is given as a 2A. And then upper wire is a 2A and 2A, so that it is 4A. And so that as we have seen, the B1, B2 is in the same directions. So the same direction. And then therefore, it should be added together. Okay. Note that in the previous case, it was a subtraction, but in this case, it's the addition. Okay, so you need to know the direction of the magnetic field, and then if you plug in the R here, then you can find out the value. So note that it is given by these units to get the right answer. Okay, now in this case, we have opposite current carrying wires. Note that here. I1 is from right to left, and then this I is from left to right, okay? The parallel wires are hung by a cord of the length 5 centimeters. Okay. And each wire has and each wire has a mass density per unit length of 40 gram per minute, and they carry the same current in opposite direction, so that it has a mass density of 40 gram per meter. Okay. What is the current if the codes hang at 11 degree with respect to the vertical? Okay, so the angle is given with respect to the vertical. So, and then here is the gravitational acceleration is given by this one. So in this case, what has to be considered is that, okay, so that the gravitational acceleration is given, that means we have to consider gravitational force. But at the same time, we can think about how the forces are generated by these two wires. Okay, that's the thing we need to think about. So we balance force per unit length for each wire because the currents are opposite in direction. The wires are repelled. Okay. So each wire is pulled sideways until the magnetic repulsion is balanced by the horizontal component of the cord tension. So it's if you look at from the side view, then there is a I, and then let's say minus I, and then it is, this is a kind of mass, and then it is balanced by the, these forces are repelling each other. And then there's a tension, and the tension has horizontal and horizontal force and uh, uh, vertical force for a given theta. And this horizontal force from the tension should be balance the force by these two wires by magnetic force. Okay, so that's the scenario. So currents are equal in magnitude, opposite direction, then it is repulsive. Okay, that is first thing. If it is same directions, the currents are acting as a kind of a attractive force. And then we need to think about each wire is displaced sideways by, okay, so let's review once again the side view. I hope I can do it with this device, etc. And this is the L, this is the L, and then this is the X. Okay, X is given by L sine theta, and that these two wires are separated by XX. Okay, so 2X, and then it's given by this one. Okay, so that's the distance between the two wires. And weight per unit length is given by, this is the gravitational force on the G. Okay, this is one. And force balance using tangent theta, that would be the horizontal magnetic force per unit length on one wire from equilibrium of the forces, tension component. Remember that. Oh, well, let's write once again. This is the vertical line, reference line. This is the wire. Well, it's not, well, let's try to erase this one. Okay, here's the reference vertical line. And that is two wires. Let's say this is the I, and this is the minus I. Okay. And then what is happening here is that it is hung by the these massless wires, okay, a massless cord, okay, and then it has a tension because it has a mass. So it has a tension, and then it is repulsed by the magnetic force. And then if you look at closely, tension, this is the theta, and that is the theta. Okay. It's the tension. And there is an upward force, T cosine theta, and there is a horizontal force, which is the T sine theta. And we note that it should be balanced by the magnetic force. Okay. And then there's another one which is acting on mg, or you will see that it is the gravitational force. So we have two cases. Vertically, tension should match with the tension, the vertical component of the tension should match the gravitational force, and the horizontal component of the tension should match the magnetic force. That's the problem set. So you need to understand the equilibrium of the forces, and then you need to identify the forces one by one. Okay, so in this case, the vertical component is the t cosine theta. So t cosine theta should be matched by with the gravitational force. Gravitational force is per unit length is shown here. Okay, and horizontal case, the horizontal force should be matched by the magnetic force, magnetic repulsion. Okay, so these are the two very important situations. And divide the horizontal by vertical. Horizontal by vertical is given by tangent theta is given by this one, so that F is doubly tangent theta. Okay. And the magnetic force per unit length between the two parallel wires are given by this one, as this one. Okay. So what we have is that I1 equal to I2. Note that this should be the magnetic force between the two current carrying wires. So you need to remember these formulas. And then in the case I1 equal to I2 equal to I, then this becomes I squared here. And then if we just plug in F equal to W tangent theta, then we have this one. And then I square is given by this value. Note that W is already known, and D is known, theta is known. Okay, so let's look at what D is. D is already there. Okay. So every parameters are known, so we can calculate the I. But once again, everything should be changed into SI unit. SI unit. So meter, kilogram, second. And then you can find out I in terms of ampere. Okay. And the next problem, a long hairpin is formed by bending an infinitely long wire. Okay, it is infinitely long. If a current of 2.8 ampere is set up in the wire, what is the magnitude of magnetic field at the point A? So apparently it's the center of this circle. Okay. Now we have a current source. We have a current source and then find out the magnetic field. So this is the typical problem. The current source is given, and then find out magnetic field. Okay. So that's the thing. So total field at A is a vector sum of the fields from the semicircular arc here from to here, and then two straight wires. Top, bottom. Note that I flows this way, so that top is in the from right to left, but in the bottom is left to right. Okay, and then the current is in these directions. Okay, so now let's look at the magnetic field from the semicircular arc. Semicircular arc, and we want to find the magnetic field here. Okay. Semicircle arc angle phi in radian, the magnetic field at the center is given by this one. Okay. And here the arc is a semicircle, so that phi equal to pi, and then you can get this value. So this formula, just please look at the lecture note and or the textbook. So you need to memorize, you need to understand this formula, first of all, to find out the magnetic field from the semicircle arc, and then magnetic field from each straight semi-infinite wire, and then the semi-infinite straight wire at a perpendicular distance r is given by this one. So because it is semi-infinite, okay, so that the distance is given by r. Distance is given by r, okay. So we know that semi-infinite straight wires, the magnetic field is given by this one, is same as, okay. And there are two such stress sections, top and bottom. And then as you could see here, I saw that. Let me just go. Let me just, top is from right to left here. So let us draw. Okay, so in this case, and the top, bottom, it's not clear to you, but let me just erase this. We want to find out the directions, whether it is addition or subtraction. So let's, if this is the case, then it's going to be, it's not, it's coming out. Okay, right. And in the case of a bottom, it is also coming out. So that it is the same direction. So magnetic field should be the same direction. So that if you add them together, it should be, because it's the same distance, R, and same current, II, so that it should be 2. Okay. And then we know the contribution from the arc and the contribution from the straight. Then you can find out the vector sum. Note that they are all the same directions. So that they are the same directions. So that the vector sum becomes scalar sum. Okay, and then we can get this one. Okay. And next problem is similar to the previous one, but it's a little bit different. So infinitely long wire is formed as in a diagram below. It is formed so that it has a circular portion. Circular portion is here, and then straight portion. Okay, and then it is distance from the wire to the center is given by small r, and the radius of the circular portion is given by capital R. Okay, we need to find out small r such that the net magnetic field center of the circular portion is 0. So here you want find out r such that this goes to equal to 0. Okay, so that's the thing we need to find out. Let's try to, before we do that, how do we do that? B equal to 0 means is that there is a cancellation of the magnetic field. Will it cancel? So that if you look at the circular loop, you will see that the magnetic field from the circular loop at this point is going to be into the pages, right? But in the case of a magnetic field from this straight wire, you will see that it is out of pages. Oh, it is opposite direction, so that you can cancel. So problem is then we need to figure out the magnetic field at this position, center of the circle, and then we need to figure out the contribution from the circle and the contribution from the straight wire. Okay, so let's try to find out magnetic field at the center from the circular portion. The full circle is given by this one at the center. So we'll be dealing with the magnetic field calculation in our classes. And then direction is out of a page. I'm sorry, in this case, this is into the pages. So this is into. And then in the case of magnetic field at the center from the straight portion is given by this one. So note that it looks very similar, but for the circular loop and the straight loop, there is a pi factor coming out, okay? So note that it is, if it is into, then it is going to be out of pages, okay? So that these two are in opposite direction. So it should be subtracted. And then if we set to have a zero magnetic field, this contribution should be equal in magnitude. Okay, and then we need to find out r, small r. Okay, and then we get this one, and then from this you can get rid of the mu zero I, and 2, and then you get this one, or even 2. And then small r is given by this factor, and then you can get the answer. So in this problem is a typical problem of for a given current source, what is the magnetic field? Okay, that is the typical questions in these problems. Now, once again, another problem comes in. A solid rod of the radius r carries a current of I equal to 6 ampere. This is the solid rod. And with a uniform current density, that means is the J is all the same across over the cross section, and the current density is given by I over area. There's also thin wire. This is the thin wire. And then point P is on the line between the two. So point P is between the two. Okay. And what is the magnitude of a current in the thin wire so that the magnetic field at the point P equals the magnetic field at the center of the rod? So we have to find out, first of all, uh, B at P, and then B at center of the rod. So let's try to find out how we can deal with this. So basically, the current sources are given, and we need to find out the magnetic field. Uh, the rod current has a 6 ampere. So let's say this is the into the page. So rod I 6 ampere. We want a thin wire current such that uh, magnetic field P at P is same as the center of the rod. Okay. Oops. Let me just. The thin wire is 2R away from the surface of the rod. The distance from the rod sensor to wire is given by 3R. Okay. So this is the rod center. This is R once again, so that we have a R, 2R, and 3R. Okay. And point P is between them at the distance R from the wire. Wire to P is given by this one. So the distance from the rod sense to P is given by 2R. Okay. So we have this distance is identified. All the distances are identified. And we need to apply the magnetic field formula, long straight wire for the thin wire at the distance small r, it is given by this one. And for the solid rod with a uniform current density, then it depends on where the our position of the interest lie inside or outside. In this case, inside the rod is going to be this one. Note that it is proportional to R. And outside, it acts like this one. It is due to the Ampere's law. Okay. Now we have to consider all the formulas one by one. So field at the center of the rod. Field at the center of the rod. So at the center, because the rod, the coordinate at the center is given as r equal to 0, so that the magnetic field of the rod's own field is 0. Only the thin wire contribute at the distance of 3r. Okay, so at the center of the rod's own field is 0, and the only contribution is from this thin wire. Okay, so distance is 3r, and then we have this one. So if IW is into the pages, this one, then you will find out the magnetic field uh, is, you'll see that it is the downward magnetic field is, so it is at the center, it is downward, okay? And now field at point P is, it has two contributions. So thin wire and rod. Note that at point P is outside the rod. Okay, that's the key point. And in contrast to the center, it is inside the rod, so that we have a two different formula for the inside and outside. Okay. So from the, we have a two contribution for at P. So magnetic field at P from the wire is given by this one. And from the rod at P is the distance 2r from the rod center outside, and it's given by this one. Okay. So if you look at this, the direction of P is left of the center, so the current into the pages. Field is upward. Okay. So if so now look at the distance, because we need to check out whether it is the opposite direction or the same direction for these two magnetic fields. So first we figure out what are the formulas for the two different magnetic field, and then because magnetic field is a vector, we need to think about whether this is going to be subtraction or addition. Okay. So now let's look at the situation. So the current from thin wire is going to be, so that it is, if you use the right hand, and then that it is magnetic field is the downward. Okay. And what about the magnetic field from the rod? Okay, so P is here. And then once again, it is going to be the same direction as the wire. And then you will see that, so that it is magnetic field is going to be upward. Okay, so that's the key things. So if wire and the solid rod has the same direction as the problem states, and then you will find out that these two magnetic fields are in opposite directions. Okay, so we know one magnetic field at the center and these two magnetic field at the point P, and then we need to get the equations correctly, so that this is the condition we need. Magnetic field at the point P is going to be same as the magnetic field at the center, okay? So magnetic field at the point P is, we note that it is the opposite direction, so that it should be negative. And then we know what the magnetic field at the center of the rod. And then we have these equations. And if you factor out all the common factors, then we get this one. And we substitute our rod is 6 amperes, okay? And then we get wire current can be found from these equations. And IW is unknown, and then you can find that this one. So this problem seems a little bit complicated because it is two types of a wire. One is the very thin, and the other one is a solid rod. And then for the solid rod, we need to figure out whether position is inside or outside the magnetic field formula would be different. That's the thing. And then we could calculate each magnetic field for different position and equate the condition like this. And then we can find out one of the unknowns. Okay, the toroid shown in the figure has a wire carrying about 7 amperes wrapped around it, was N is given by these times. And the inner radius R1 and R2 is given. What is the magnitude of magnetic field along a circle that has halfway between the inner A, here. So halfway between the inner and outer edges of the toroid. So if you look at it, we need to find out the Ampere's law. So we have a closed loop, and it's going to be same as this integral is going to be same as the current enclosed by this closed loop. And we are going to choose a circular Amperian loop of radius r inside the toroid. And this is our closed loop, Amperian loop. Okay. And then we note that we'll have a constant magnetic field, and then it's going to be 2 pi r. If you integrate over this Amperian circle, then you will find out that if you do the integral, then you will get the length of the arc of the circles. But we have and then in this case, we have an enclosed current here is that the current is this. Okay, and you have n turns, and then each of the coil has a current I, and then we get this one. Okay, and then we get this relationship. And then we need to calculate the numerical calculations here. So it says that it's a midpoint between the inner and outer radius of the toroid, so that it is going to be this one. And then we get this result. And then if you just plug in the number of turns, ampere, and the meter, then you can get the magnetic field in Tesla. Okay, here is another example. The wire 1 in the figure below is oriented along the y-axis and carries the current I1. A rectangular loop located A equal 2 to the right of the wire and in the xy plane and carries another I2. So that we have 2 wires carrying currents. So that we need to think about magnetic field, okay? And then the magnetic field, and there's a loop, and then it means it carries a kind of a force. Find the magnitude of the magnetic force exerted by the wire 1 on the top of a wire length equal V equal to 7 in the loop here. So this is the force we need to figure out. So in the figure, it is already given some of the indication of the vector. So the current wire 1 will generate the magnetic field. Okay, so it's coming out of paper and they're coming into the papers. Okay, so that it has this coming into the papers direction. This is the magnetic field generated by the wire 1. And then here is the top wire. top wire. And then we need to figure out what is the magnetic field, induced force, FB, on the top of this wire. So each element, it works as a F magnetic field. Force is given by I dl df is ideal times B. But note that current and the magnetic field is orthogonal, so that we do not have to plug in any sine theta. And this is the infinitesimal force acting on the top wire. Let's try to find out one by one. So first one is that magnetic field produced by the long straight wire, wire 1, and then it is given by this formula. Okay. And the geometry of the top segment is left side at the distance A. So A from Y1, and the top segment runs horizontally from x equal to A to x equal to A plus B. Okay, that is the range we are going to consider. And then once it is given, we know that is infinitesimal current acting on the top wire is going to be this one. Note that here is the I2. So B is from I1. So our current I1 is generating magnetic field, and the current on the top element of the loop is interacting with this magnetic field to result in the force. So note that it is from the B1. And then you can see that is given by this element. And then this should be df is going to be this one. And it's time to think about sine theta equal to 0, sine theta equal to 1, because sine theta angle is orthogonal to each other, so that sine theta becomes 1. And then the only thing is the given by this one. Okay. And on the top, so is along the x directions. So it is dl is dx. Okay. And then here is the I1. The current is going to be like this, so that it depends on the position. So that's the reason why we put the Bx. Now let's try to find out what it is. Bx is nothing but, you just plug in here. So if we have a position x, and then it's going to be user I1 over 2 pi x. So we have this one. It's from the wire, magnetic field from the wire at the position of x, and this is the case. And then if you integrate from x equal to a plus b for the top wire, and then you do the integral, and then you get the log. Okay. So this is the answer. And if you plug in the right numbers, you will get the force in Newton. Of course, I1, I2 should be in ampere. Okay, and this is the number. That's it. Okay. So in this case, it's an interesting problem. So it deals with the interaction between the magnetic field and the current carrying a wire. So in this case, first case is that we need to figure out the magnetic field. magnetic field from the wire. Here is the B. And then it is as a function of x, Ex. And then on this x, ds is the same as dx. And then we need to figure out infinitesimal force on this segment, okay, on the top of this loop. And then we can find out the force law. So first we need to find out the magnetic field. And then we apply the force law. And then we do the integral for the given section from a to a plus b. And then we get the final answer. A long cylindrical conductor of the radius carries the current I equal to this one. And current density is given as J equal to BR. In the actual problems, the B is given, but I found out that B is misleading. If you just plug in the B, it does not give you the current. So what we are going to do is that we are going to set B is a kind of unknown, and then we will do the problems. Find the magnitude of the magnetic field B at the distance R1 equal to 0.7 centimeters, which is the inside, and R2 equal to 50 centimeters outside of the cylindrical conductor. So we are given a certain current density, which will give us this total current. Okay. And then we need to find out magnetic field at the position R1, which is inside, and R2, which is outside. So in this case, let's try to find out the B first. In this case, we are going to have this thin ring. So 2 pi r times dr is our area element. And the di is given by jr times dA is jr is given by br, so that it is given by this one. And then current is given by current enclosed within the radius r is given by this one. So if you do the integral, this is j r dA, and then it's going to be this one. And total current at R equal to capital R, the total current, which is given by this one, is going to be this one. Okay? So that our parameter B should be this one to have a charge conservation. So now, if you just plug in this B into the current enclosed by the radius R is given by this one. Okay, this is R. Current is important to find out the magnetic field. So using Ampere's law, this is the closed loop of the magnetic field. Over the closed loop is going to be our enclosed current, okay? Because this is our formula. And R1 equal to 0.007 meter. This is inside the conductor. The inside the conductor I current is given by this one. So that we can just calculate this formula, and from this we can calculate the magnetic field. And for the R2, which is outside, and then I is the value which is given, okay? so that we can get BL2 here. So note that we need to find out inside magnetic field and outside magnetic field. And then if the current density is not a constant, we have to satisfy this one. Total current density, this is going to be this one, okay? And then we can eliminate unknown B, and then from this we can find out, we can apply the Ampere's law to find out the magnetic field inside and outside. Okay, so a thin, infinitely large sheet lying in the YZ, okay, so carries a current linear density of this much. The current is in the Y direction, okay. So in other words, it looks like a kind of a something like this, okay. So if you look at it, it looks like a kind of a J, and it looks like a sigma. So sheet current density. This is sheet charge density. And then we have these two cases. E is given by sigma over 2 epsilon naught. And then you will find out that in a similar manner, magnetic field will be also given. So first thing is that we need to have an Ampere's law. Okay. Choose a rectangular Amperian loop that straddles in the sheet and cell. Look at this this one. Cell. And then it is passing through. So this is our Amperian loop. And then you are going to apply this Amperian loop. And then we need to find out the enclosed current. Okay. So here is the sum of the assumption we are going to have. We are going to have a W and length L, because if this is the case, note that if the current is this, then the magnetic field would be something like this, okay? So that on this side it is a kind of a parallel to each other, but in this case it is, if you notice the case, you will find out that the short sides are perpendicular to the B, okay? This direction, so that it is it's perpendicular to this magnetic field, not that, so that we can consider only the two sides, okay? So that is going to be B times L, B times L, 2BL. And then enclosed current is given by JB times L. This is the and apply the Ampere's law, you will find out is given by IJS, okay, sheet current density. So it is very similar to the electric field for the current charge density, sheet charge density. It is given by sigma over 2 epsilon naught, okay. JS. Sigma S. Okay, so it is kind of a symmetric, and you can find the magnetic field values here. And finally, we have a long straight wire of a radius of 19 centimeters, and it carries a current steady current density of 3 ampere. It is uniformly distributed. And calculate the magnitude of magnetic field at the distance 1 centimeters to the inside and 40 centimeters, which is outside. So once again, we are going to apply the Ampere's law, but the difference between the previous problem is that now we have a uniform charge density. So in this case, it is given by the Ampere's law, so enclosed. Okay. And so in this case, note that we have a uniform current density. J is given by I over A is a constant, which is I over pi R square. Okay, and then enclosed is given by, so that total area divided by the area inside the radius R is given by this one. So enclosed is given by this one. So the magnetic field is proportional to the radial distance. But in the case of outside, total enclosed current is total area, total current I. Okay, so that we have a given by this one, so that it is inversely proportional to R. Okay, so that's the two contrast. And then if you just plug in the numbers one by one, then you can find the magnetic field and etc. So now the final problem is the magnitude of magnetic field at point O here for these configurations. Okay. So we need to find out magnetic field at here. So each of them is carrying the I, and then we need to find out that this is the current source, and then we need to find out the magnetic field. And let's try to divide. Is that the two straight wire, and then the straight wire portion lie along the radial lines of O. So note that this portion is on the radial directions. Note that in the Biot-Savart law, if you have a current density in a certain ds, if this is the same as is parallel to the R vector, R unit vector, then you'll get the zero component, because phi is going to be 0. And then, so that these two elements will not contribute any magnetic field at position O. Okay, this is because of this vector product. A cross A is always 0. Okay? And the only portion contributed to magnetic field is this circular path. Okay, so that's the thing we need to figure out. So magnetic field at the center due to the circular arc is given by this one. And then you can find out the magnetic field. It's fairly simple, but apparently it looks complicated. But if you look at the radial vectors and the current distribution, you'll find that these two wires does not contribute and only the arc will contribute. And apply the arc magnetic field law and then you will find out what it is. Okay, that's it.